Hello, everyone. My name is José Santos. I am a faculty member in the Department of Animal Sciences at the University of Florida. And for the next 30 minutes, we're going to discuss a few important topics related to feed efficiency in dairy cattle. I want to acknowledge my collaborator here, Mariana Nemi Marinho. She is a PhD student working with me, and I'm going to show a lot of the data that she developed during her master's and early in her PhD program. So if you look at milk production over the years, and the example I'm going to use is the US dairy industry, but probably this applies to almost any country in the world that uses confinement systems and intensive milk production. What we have seen is this steady increase in production per cow. Here in the y-axis, I have pounds per cow per lactation. So here would be the equivalent of 10,000 kilograms of milk. And you can see that over the years, these cows actually increased production approximately 150 kilograms. Part of that has been genetic improvement. Part of that has been management, which includes nutrition, health, cow comfort, and everything we do to enhance animal performance. So with this increase in milk production, there has been a steady increase in feed efficiency. And it's a simple concept to understand. So if we look at a cow in the 1960s, in the US industry, this would be a prototype, a shorter cow, more fleshy, but a cow that produced a little less than 5,000 kilograms per lactation. Over the years, we changed the phenotype of this cow, and obviously we changed the ability to produce milk. So the cow born in 2018 to the just recently, she is expected to produce on average 11,500 kilograms. Obviously, her genetic potential is larger than that, so there are limitations. And the reasons for those changes have been, among others, genetic selection. So we've selected animals to have increased production. We have improved nutrition, diet formulation. We have improved cow comfort. So all of those factors together are responsible for this large change in production per cow, and with that, an increase in feed efficiency. However, our cows, with the improvement in production, they became larger, and they also have greater dry matter intake, as you will see. So let's just look at this concept here that was put together by a group at Cornell University. So if you look at a cow that produced very little milk per day, 7 kilograms, you can see of the total nutrient intake, and here it's based on calories, the energy intake of that animal, or the energy required by that animal. 70% would be used for her maintenance. But as production increase, if we look at a cow with 30 kilograms of production per day, which is a pretty average cow, you can see now that she diverts 2/3 of her nutrient needs to production and 1/3 to maintenance. So as production increase, there's been this dilution of maintenance, which has favored more nutrients being partitioned to production. With that, this cow has also become larger. So if you look at this figure here, the year that's listed in the x-axis as 0 represents the birth year of the cow of 1970, and here would be 40 years later, equivalent to 2010. So you can see the cows have become heavier, so they're basically larger, okay? And they also have to eat more dry matter. So dry matter intake has to go up to support the increased nutrient needs for lactation. But with this increase in dry matter intake, the retention time in the rumen has decreased. So for cows of a given size to consume more dry matter, passage through the gastrointestinal tract has to be faster. And with that, the opportunity to digest nutrients, particularly in the rumen, decreases, as we can see here. In addition to that, the cow has become larger, therefore her metabolic body weight has also increased. And with that, the maintenance needs have increased. And just recently, the new National Research Council, which is now labeled as National Academies of Science and Engineering and Medicine, has suggested that the amount of calories needed per kilogram of metabolic weight is slightly greater than originally thought, probably because of other activities than just based on metabolic rate. So activities such as the immune system, physical activity, etc. So let's just look at this from a cow's perspective. Imagine this cow here that has this gastrointestinal tract represent on her left side. As she eats, the rumen fills up. So in this increased content in the gastrointestinal tract, until a certain point when there is perhaps a maximum rumen fill in this animal. So now this feed has to leave the rumen in order for the cow to be hungry again and have appetite. And now this gastrointestinal tract empties. Okay, so as cows consume more feed, the rate of retention of feed in the rumen has decreased, and part of that might explain a reduction in dry matter digestibility, meaning that the ability of the cow to extract nutrients from the feed as intake goes up would be expected to be less. In addition, I mentioned to you that maintenance requirements have increased with larger cows and perhaps with the activities they have. So just to put this in actual numbers, if we look at a cow that weighs 700 kilograms, her metabolic body weight would be that body weight to the power of 0.75. Initially, we thought that this cow would require 80 kilocalories per kilogram of metabolic weight, or 0.08 megacalories. So this cow would have to consume about 11 megacalories per day just for her maintenance. So if you think of a typical lactating cow diet, that would represent 6.5 kilograms of dry matter a day for her maintenance. So if we look at the current values that we are using, at least in the North American industry, this cow now requires 13.6 megacalories of net energy for lactation per day. And this would be equivalent to 8.1 kilograms of dry matter of a typical lactating cow diet. So you can see that the changes in maintenance requirement will increase the amount of dry matter the cow has to eat just to support her day-to-day activities, regardless of her production. So that's one component. But there are things that affect how nutrients are utilized. So let's look at this energy partition scheme here that is pretty standard in nutrition classes. So we have feeds that have their gross energy content. Once these feeds are consumed, energy can be lost as feces, okay, so undigested material. It can be lost as gas, for example, methane. It can be lost as organic products in urine, or it can be lost as heat of digestion or heat of metabolization of feeds. And then we have what's called the net energy of the feed, what can be used by the animal. And that can be either captured as milk or body tissue, or it can be used for the maintenance of the animal. So this is where milk would be produced. So as nutrients are partitioned to synthesis of tissues, we would support milk production. As nutrients are partitioned to maintenance, then less would be available for production. Obviously, we want to divert as much as possible to production without compromising the cow. Okay, so to improve the proportion of feed energy captured in milk, we have to increase milk production relative to her maintenance, and we have to increase the conversion of this gross energy into net energy. Okay, so here, to increase this first component here, we would have to dilute her maintenance, which is what we've been doing by selecting for more productive cows. But if we want to increase the conversion of gross energy to net energy, we have to alter this portion of this scheme here. And this is where we would alter the cow to be able to extract more nutrients from feed. For instance, to use nutrients more efficiently. And that's what we're going to talk about in the next portion of the presentation. So let's think for a minute how we calculate feed efficiency. At the farm, this is what we use. Okay, we look at the yield of milk. In the US, we focus more on what's called energy corrected milk. In other places, maybe just kilograms of milk solids, such as fat and protein. but here we typically use energy-corrected milk, which is a milk adjusted for a certain amount of fat and protein. So the equivalent of a milk with 3.5% fat and 3.1% true protein. And we look at the amount of milk produced per kilogram of dry matter consumed. So this is commonly used on farms and it's very useful, but there is a problem because it does not account for changes in body energy. For example, loss or gain of body tissue, okay? So if we look at gross feed efficiency, cows in early lactation are very efficient because they lose body tissue and they lose to support lactation. Whereas cows in mid to late lactation, they gain body tissue. So a portion of the energy consumed is never used for milk synthesis, okay? And this component here relies on dilution of maintenance. Now let's look at a second component, which is typically what we use to calculate feed efficiency on individuals, and that's what I'm going to focus for the remainder of my presentation. This is called residual feed intake. And as the name says, this is the residual from a mathematical calculation, meaning that this is the difference between the observed intake of the animal minus the expected intake given a certain set of parameters, okay? And the parameters that we use are the energy required for milk synthesis. So let's think of the energy-corrected milk. The maintenance needs of the cow, which to a large extent is her size or her metabolic body weight, and the tissue accretion or loss, whether that cow is losing or gaining body weight. And this is adjusted for the cohort. Think of the farm, or in my case that I do experiments would be the experiment or the diet or the combination of those factors. So by default, by using this to calculate the expected dry matter intake, more efficient cows, those that eat less than expected, they are also expected to have the same production and the same body tissue changes, because by default, the residuals are independent of the predictors in this equation. And you will see some of those results in the following slides. Okay, so let's talk about some of the factors that affect feed efficiency, and there are many of them. And just for the sake of time, I'm going to give you 3 examples, okay? And I think these are probably the most important examples, okay, that we can influence feed efficiency. One of them is cow health. It's preventing disease because disease are catabolic and they alter the partition of nutrients. The other one is diet formulation, and there are many ways to influence efficiency through diet formulation. I'm going to give one example. And lastly, I'm going to focus on the intrinsic ability of the cow to utilize nutrients. So let's look at this figure here that was put together by Alex Bach, a scientist in Spain, in which he looked at milk energy secretion by cows, so the amount of megacalories produced per day as milk, relative to the energy consumed above the maintenance needs of the animal. So in this case, it's accounting to some extent for the body energy changes. And he pulled data from 51 experiments. So if things follow the expected pattern, this relationship would be linear and would follow this dashed line here, okay? But what he observed was this relationship here, okay? So in a theoretical line, there would be 1-to-1 efficiency of net energy use above maintenance needs of the cow to be utilized for milk energy synthesis. But what he observed was that as production increased, meaning as energy consumption increased, dry matter intake increased, the efficiency of use decreased. So simply selecting for more productive cows, eventually we're going to lose the ability to completely dilute maintenance requirements because the ability to utilize nutrients perhaps will decrease. So we need to think about other opportunities to improve feed efficiency. So let me show you one opportunity to improve feed efficiency by reducing disease. And this is a very cool experiment done by scientists at Oklahoma State University. So they used this multi-catheterized steer model. So these animals had catheters in the hepatic vein, Okay, so everything that gets drained through the portal drain viscera gets to the liver, and then that leaves the liver through the hepatic vein. They had catheters placed in the portal vein so they can measure concentration of nutrients in the portal vein coming from the gastrointestinal tract, and they had catheters in the mesenteric vein and artery. And by using a dye or a marker, they were able to calculate blood flow, and then by venous arterial difference, they can calculate the flux of nutrients across different tissues of the gastrointestinal tract. So here's a picture of those animals from a slide that was provided to me by Clint Cribble. So if we look at this here, I'm going to make a parallel between the model they use, which is a inflammatory response in the respiratory tract. So they basically challenge animals intratracheally with Mannheimia haemolytica, so the old Pastorella haemolytica, to induce an inflammatory response, versus the control that received just sterile saline in the trachea. But I'm going to make a parallel to a cow that has another disease that's also of acute nature, metritis, which affects probably too many of the dairy cows today. Anywhere from 20 to 30% in our industry are diagnosed with metritis. And these cows have the same hallmarks of inflammatory response as this steer with respiratory disease. So for lack of data, I'm going to use the information from the steers. So here is one of the results of the work they've done. So here we have the amino acid flux across the liver. Okay. And this is segregated into essential amino acids, those that the tissue cannot synthesize, and those that the tissue can synthesize, the non-essential amino acids. Okay. Every time the bar falls below the 0 value, it means that the tissue, in this case, the liver, is secreting less of that nutrient that is taken up. So the net flux is negative, and the flux here is in millimoles per hour. So we can see that the control animals have a negative net flux of essential amino acids, which makes sense because these amino acids cannot be synthesized by the hepatic cell. But we can also see that the challenge animals have a greater negative net flux of essential amino acids. So when we look at the non-essential amino acids from their data, now we see a positive net flux in the control animals, but the challenge animals, they remain with a negative net flux. So when they put these two together, you can see that there is a big difference between the two. And if we do a quick calculation using the average molecular weight of the average amino acid, protein synthesizing amino acid of all 20 of them, this difference here would be equivalent to 2.6 moles of amino acids per day over a 24-hour period. And this is almost 400 grams of metabolizable amino acids. So amino acids that are in the circulation for this 400 kilogram steer. If we translate this to a lactating dairy cow with a 67% efficiency of use of metabolizable amino acids to incorporate into what we call net protein, which is the protein present in milk protein, this would be the protein equivalent present in 8 kilograms of milk. So you can see that disease would utilize nutrients and divert them away from production. Not only disease causes lack of appetite, which automatically reduces production, but also increase the use of nutrients from favoring survival and against productive functions. And that would obviously reduce feed efficiency. The second example I'm going to show you is through diet formulation. And there are many ways to manipulate diet to improve efficiency, okay, such as forage quality, ionophores, feed additives. I'm going to use one example here because this is a compilation of data from multiple experiments, so it has a lot of external validity. So this is a meta-analysis from the group at Michigan State University in which they looked at supplementation of fatty acids using calcium salts of palm fatty acids. You can see the increment, the mean increment in fatty acid content in the diet. So the control diets had an average of 3.45. The treated diets that included some level of calcium salt of palm fatty acids, the fatty acid content increased by about 1.57 percentage units. So this is what they found. Cows ate a little less, maybe 0.6 kilograms less. I think that was the mean value. They produce more milk. They produce more energy-corrected milk. They did not change their body weight changes, so they were the same. They lost a little bit of weight. I'm sorry, this is the difference between the treated relative to the control. So no difference in body weight change relative to the two treatments. And you can see here that the amount of energy-correct milk per kilogram of dry matter intake increased. And I think this increment was about 60 grams more energy-correct milk for every kilogram of dry matter intake, maybe 60 or 70 grams. So here's an example of manipulating the diet to improve efficiency by doing two things: increasing energy-corrected milk at the same time that dry matter intake is less, just because the diet contains more nutrients, at the same time that they did not affect body tissue reserves. Okay. So 80 grams of energy-correct milk per kilogram of dry matter intake. Now, let me move from the things that we do in the diet, in the health of the cow, and now let's think a little bit about this direct trait to measure feed efficiency, and maybe how we can manipulate that, which is called residual feed intake. This is a trait that measures feed conversion efficiency after we adjust for other factors that are listed here, okay? That are listed here. So basically what this is you generate a model to predict dry matter intake, and then you look at the deviation from the model, okay? So let's look at this cow here. This cow was expected to consume about 50 pounds of dry matter, so about 22.5 kilograms per day, but she actually consumed 35 or 36 pounds of dry matter. So she only ate about 16 or 17 kilograms per day. If you look at this cow now here, she also was expected to consume approximately 53 or 54 pounds of dry matter, so 23 kilograms, but she ate 63 pounds. So she is not very efficient cow. So the points above the line are those less efficient cows. The points below the line are those that are the more efficient cows. If a point falls in the line, it means that the model predicts perfectly the dry matter intake of that cow, so the residual would be 0, okay? So that's what we did in this particular study here. We calculate residual dry matter intake. And we were interested in looking at the cows that had negative relative to the positive cows. So why is that? Well, because residual feed intake has genetic variability. It's not only phenotypic variability, but there is genetic variability. It has a very decent heritability, so it can be transmitted from one generation to the next. So it's controlled by genes. Obviously, feed is very important because it represents 50% or more of the cost of production in most dairy farms. Okay, so here you can see the genetic variability of RFI, which I'm going to use from now on, in terms of predicting transmitting ability, what gets transferred from one generation to the next by either the sire or the dam. So in this case, these are sires. And you can see that there are sires that have negative RFI, and there are sires in the industry today that have positive RFI. Okay, so the range goes from minus 360 pounds per lactation, so minus 150 kilos, to plus 385 pounds per lactation, so to plus 160 kilos. So there's a 300 or 400 kilogram spread from the most efficient to the least efficient sires in terms of transmitting their genetics to improve feed efficiency in the daughters. So you might be thinking, is this 0.14 heritability a good value? So if you look at heritability for milk, it's 20%. For fat, it's 20%. For fitness traits, it's much smaller. You know, it's in the 1 digit. 3%, 1.4%, 4% daughter fertility. So yes, this is actually quite large heritability from the genetic point of view. So we can select for that. So let's look at this cow here, for example. This is a cow in one of Mariana's experiments. So this cow produced an average of 48 kilograms of energy cracked milk over a period of 20 weeks in the experiment. She consumed 21 kilograms per day. I'm sorry, this should be kilograms per day, but her expected dry matter intake was 24 kilograms per day. So she had a residual feed intake negative 3 kilograms. So if we think a current feed costs, at least here in the US, this 3 kilograms would represent a 96 cents saved dollars per day. And for that cow in her lactation would represent a little over $300 savings relative to the average cow in the herd. Okay, so obviously she is a more productive cow. She's a more profitable cow because she can do she can produce milk with less input. So can we identify these superior cows? So some of the questions we have asked is RFI repeatable across lactation stages? So is what happens in mid-lactation also what happens in early lactation? And this RFI impact tissue mobilization, health, and reproduction of cows. Why we ask those things? Because as cows eat less, if we calculate energy balance, it's going to be smaller, yeah, because energy balance is driven by dry matter intake. Eating less by default will reduce energy balance. So the objectives of the studies that I will present to you now are to determine the associations between ranking of RFI in mid-lactation with measures of body tissue mobilization, production, and risk of disease and survival. And then I'll show you the associations with reproduction in hosting cows. So we conducted 2 studies. The first one, we used data from almost 400 cows in which we had daily dry matter intake for the first 105 days in lactation with daily body weights, daily milk production, twice a week milk composition, and twice a week body condition score. So we could calculate residual feed intake. In the second study, we looked at data from a little over 800 cows, and we had exactly the same type of data: daily dry matter intake, daily body weights, twice a week milk composition, daily milk yield, and twice a week body condition score, in addition to the responses of interest that I'll show you. So the way we predict dry matter intake was looking at the amount of milk energy secreted, the body weight to the power of 0.75, which is the metabolic body weight, the body energy change, and this is the change in body weight associated with body condition score. In other words, a negative value means that the cow lost weight, a positive value means that the cow gained weight. And we adjust for the body score with the assumption that a fat cow, each kilogram of body weight has more calories than a skinny cow, just because of the tissue composition. And then we adjust for the cohort, and we calculate RFI based on the observed minus the predicted intake. So the deviation from what this cow was expected to eat, given all the set of predictors here. So then we follow those cows in terms of incidence of disease in the first 90 days. We had all the information for the first 15 weeks of lactation, and we follow survival and reproduction for the first 300 days postpartum. Okay, so this is RFI in mid-lactation. We segregate cows into quartiles. These are the most efficient cows. These are the least efficient cows. So these cows ate less than predicted. These cows ate more than predicted. And then we looked at what happened in the first 5 weeks of lactation in those cows. So the data that I'm presenting here is the data from the first 35 days in milk. You can see that ranking cows based on RFI in mid-lactation was able to segregate more efficient cows also in early lactation. Okay, so these cows ate less in early lactation than the least efficient cows. However, if we look at the body energy change or the body weight change, we didn't detect any difference, although the energy balance was smaller as expected, and I mentioned to you. Okay, these cows produce the same energy-corrected milk, as you can see here, no statistical difference between them, and they mobilize the same amount of body tissue. Okay, and obviously because they were more efficient cows, they incorporate more of the dietary nitrogen into milk, nitrogen, and tissue than the least efficient cows. So in fact, selecting for improved RFI in meat lactation will also improve, or we expect to also improve efficiency in early lactation without compromising measures of body tissue mobilization. So if you look at performance of those cows, here are the most efficient cows, the quartile 1. They eat less throughout. These are the least efficient cows, the quartile 4. They eat more, but they produce the same amount of energy-corrected milk, no difference, okay? And if you look at their gross feed efficiency, it's always better for the quartile 1 cows compared to the quartile 4 throughout the period of observation. So a common question that people ask is that, well, this may affect health of the cows. So we look at incidence of disease in the first 90 days, including retained placenta, metritis, mastitis, displaced double mason, and others, as well as somatic cell score. And you can see that they did not differ among quartiles for all the responses that we evaluate. So much so that when we looked at survival by 300 days postpartum, it was not different among treatments. So no indication that more efficient cows would suffer relative to their health in early lactation. Now, here's a very important point. As residual feed intake becomes negative, net energy balance decreases. That's exactly what we expect. But look at what happens to the body energy change. It really does not change at all. So the amount of tissue energy mobilized by cows that were more efficient or less efficient was irrespective of the residual feed intake, okay? But energy balance has a weakness, which is we assume that the ability of cows to extract energy from feed to be the same and all based on the composition and nutritional composition of the feed. But we know that some cows are better able to digest and use nutrients. Some cows have less energy requirements for maintenance, and those are likely to be the cows with negative residual feed intake. Okay. So is this residual feed intake repeatable between different stages of lactation? And the answer is yes. So here are the ranking of cows in terms of residual dry matter intake in mid lactation relative to early lactation. You can see that this relationship is positive and linear, although there is some re-ranking, but there is a good correlation of 43 on a Pearson correlation and 32 on a Spearman correlation. So they are related. So more efficient cows in mid lactation are also more efficient in early lactation, although there will be some re-ranking of animals. Now, what happens to reproduction? So remember that we follow 850 cows. We took the same approach, ranked them based on residual feed intake in mid lactation as the most efficient and least efficient. There's a little over 200 cows in each group. If you look at the proportion of cows that receive insemination in that lactation, did not differ. So 98% of them receive at least one AI. We had multiple pregnancy diagnoses, showing you the data after the diagnosis on day 74 after insemination. So we account for the losses of pregnancy. Here's a surprising thing. Remember that this more efficient cows, they have smaller energy balance, okay, than the most efficient, than the least efficient cows. These cows here have greater energy balance, okay? So you would expect that maybe these cows would have better reproduction, but they didn't, okay? Pregnancy at first AI was less for the least efficient cows, 5 percentage points. Pregnancy at the second AI was less, and here we see a big difference. So here we saw just a numerical difference. Here we see a big statistical effect. If we look at all inseminations in that lactation, then we also see a decrease in pregnancy per insemination, meaning that if I breed 100 cows in this group, I get 31, 32 pregnancies. Here I get only 24.5 pregnancies. So by 300 days postpartum, we had more pregnant animals in the more efficient quartiles than the least efficient quartile. And this is a metric that we use commonly in the US. It's called 21-day cycle pregnancy rate. So every 21 days, a non-pregnant cow that has passed the voluntary waiting period and the farm wants to breed, she is eligible to become pregnant. You can see that the rate of pregnancy was greater in the most efficient cows compared to the least efficient cows. Okay, so as opposed to what we would anticipate, the more efficient cows also had improved reproduction despite consuming less feed. So just to summarize, if we look at this most efficient quartile of cows, they ate less and produced the same energy correct milk. The least efficient cows ate more and also produced the same amount of energy correct milk. But not only that, they had reduced reproductive performance. So this was a less efficient in terms of nutrient utilization, but also less efficient in terms of other aspects. So a cow that costs you more money as a producer. So can we select for RFI? I think that's an important question we should ask. And the answer is yes. In the US industry, as well as in many industries in the world, we are doing this. We are creating reference population of animals. So we are measuring feed intake in cows to use that. And then we are genotyping those cows to identify genomic markers, okay, or changes in what we call the SNPs or haplotypes that are linked to this variability in their genetic ability to consume nutrients and produce milk, but some consume less, some consume more. And then smart people who are smarter than me, they develop equations to predict those responses based on the markers that best explain the variability in residual feed intake. So let's see this example here, and this applies to the US industry. In the US, we have a big database for what we call body weight composite, which is basically the size of the cow. There are millions of records for that. However, for residual feed intake, we only have data from 13,000 cows today in the database because it is labor intensive and expensive to measure dry matter intake of cows. So the US industry decided to create a phenotype that's called feed saved, okay? And feed saved is a combination between residual feed intake and body weight composite. So it has a component which is RFI, and it has a component in the calculation which is the body size of the cow, okay? And in general, positive values are favorable. So the values that you will see in terms of numbers or pounds are in pounds of feed that's saved per lactation for that animal. So let's look at this 3 cows here. And let's look at this 3rd cow here, which is an animal that has a smaller body size. Therefore, she should have less maintenance requirement. She produces the same milk, about 11,500 kilograms in lactation. This is her expected dry matter intake based on the genetics of that cow. So she has a feed intake that is negative in terms of residual, okay? So this would be your average cow. She eats as much as she is expected. This is a cow with a positive RFI. She is a less efficient cow. She eats more. And this is a cow that eats less. She has a negative RFI. So when you apply those numbers to this equation, you get a feed saved of 428 pounds per lactation, approximately 180 kilograms of feed that's saved for a cow that if she has the same genetic merit for production, she would produce the same milk, but with less feed. And that's what we are looking for, okay? So is this safe, selecting for feed safe? Because as you can see, we will select for smaller animals. So we expect these cows to reduce in body size if we emphasize feed save over the years. And that's the expectation in the US industry. And some people are worried about that. But if you look at the genetic relationships, or what we call genetic correlation between body size and production, it's actually negative. From the genetic point of view, selecting for larger cows is a bad decision because that is genetically negatively correlated with production. However, if you feed animals better for a better development in terms of phenotype, obviously those animals will be more productive. So I think selecting for large animals does not favor milk yield. So we should not be too concerned with this, because we'll be able to figure out fairly quickly if we're going in the right direction or not. So I showed you genetic variability for residual feed intake. Now I'm showing you genetic variability in terms of PTA, predicted transmitting ability of sires that are available today in the hosting breed, for feed saved, which combines body weight composite and RFI. And you can see that there is a large genetic variability. There are animals that are more or less efficient relative to the ability to transmit that to their daughters in terms of feed consumption for each kilogram of milk produced. So at the end of the day, we are really looking for this group of animals here. Okay, let me explain to you this figure. So here we have observed dry matter intake. And here is the predicted dry matter intake. This is what we predict that they should eat. Okay, so if the cow falls on the line, it means that the predicted intake is exactly the same as the observed intake. If she is above the line, it means that she ate more than predicted. Okay, so for instance, this cow here ate 32 kilograms, but she was predicted to eat 23 kilograms. Okay, the cows that are above this line here are those that produce more than 40 kilograms of energy cracked milk. The ones that are below this line, they produce less than 40 kilograms of energy cracked milk. So I mentioned to you that we want these cows, and the reason being is because they are below this line here, this diagonal line, so they are more efficient. They eat less than predicted, but they are more productive. These are the high producing cows that are capable of converting feed into milk, but still produce a lot of milk. We do not want to have efficient cows that don't produce milk. Okay, in our systems of intensive production, we want high production, but we also want high feed efficiency. So I want to thank my collaborators and the funding for the projects some of the projects that I showed you. These are the students who generate a lot of the data that I shared with you today. And these are the agencies that provide funding for partial funding for those projects. So thank you very much, and I appreciate your attention.